Well, great. And uh, there's been a lot of discussion over the last few days around storage resources, efficiency, how to calculate that, the meaning of it, if we should calculate it, and so on. And one of the framings that I like to provide for that discussion is a lot of the uncertainty and an argument, if you will, arises from um, uh, the combined interest in estimating how much storage resource there is. So these are the storage resource estimates that we're probably most familiar with, very rigorously carried out in a number of national and regional efforts around the world at this stage. And the question around uh, how quickly we can use that storage resource. And that's really what this presentation is about, or this research is about. We are trying to use this information in the service of understanding what the limits are to regional and global scale-up of CO2 storage. So within that context, we have developed two groups of models to address the leading potential limitations. And those are summarized here. One group of models implements aggregate techno-economic constraints to development. So you can think of the constraints imposed by the need to develop infrastructure, to arrange financing, to overcome regulatory processes. And these models are not governed by physics, they are necessarily empirical. And so I'll talk about that first. And the other group of models that's more familiar to the communities that I'm normally working in are the physics-based models. And so there are constraints, as we've heard, imposed on how quickly we can inject, from the pressurization of the system, potential limits from the intersection of migrating plumes to legacy wells and other risk leakage pathways, and so on. And so another group of models I've been working on developing, so I'll carry you through that. So for those of you that work in physical sciences, it may come as news that these aggregate techno-economic limitations to growth, while they don't follow physical laws, actually follow well-trod patterns that can be quantified. So I'm showing here slides from two studies, one from Philip Ringrose and Tip Meckel, in which they compiled information on the rate of well construction in hydrocarbon provinces around the world, and asked the question as to whether or not that tells us if we can succeed in constructing wells fast enough for the scale of CO2 storage that we're envisioning. So you could imagine how this could be an extremely useful empirical model actually to input into simulations of scale up from CO2 storage. Here's another analog that has been used in this way from Joe Lane and others, where they used the production of oil and gas around the world as an empirical analog. And again, these data sets with some conversion to CO2 storage can be used directly actually to consider or come up with trajectories for the growth in CO2 storage. But there is an entire discipline actually that has matured around using this kind of empirical information in a more generalized and abstract way. And so what I'll just generally refer to as growth models are very simple mathematical models. This is the ones that we're using are 3-parameter models. And they represent these patterns of growth that you can see in analog industries. And the value of this is that you don't have to rely on a single empirical data set. You can abstract the growth patterns that you see in those data sets and evaluate the range of growth patterns that you see more probabilistically. So I'll just give a very simple overview of how they work. What you can see here is if we're scaling up CO2 storage, cumulative storage, we need a starting point. For this, we can use directly information on where we are now with CO2 storage. This is actually one of the original motivations of the London Register of Carbon Dioxide Storage, is we just wanted information about how much carbon dioxide was being stored now. The second parameterization comes from this industrial analog that I just described, and we can take this information and essentially fit a growth curve to this type of data and use that to shape the scale-up of the CO2 storage from the starting point towards the ending point, which is now where our resource assessments come into play around the world. And so this is a very simple framework, which is what's really needed at the resolution that we're talking about, but it's very powerful because it's very difficult to argue that you are not going to start here, that you're not able to end here, and that the trajectories in between aren't constrained by some pattern of historical analog that has been viewed. So that's how the techno-economic models work. Of course, those models incorporate one physical attribute, which is the storage resource assessed as kind of static value, and they don't incorporate this potential limitation from the dynamic constraints arising from the physics. So injectivity, the pressurization of the reservoir, these are really the dominant constraints that we've been looking at and incorporating into these models, but of course we have plume migration and potential leakage pathways. And fortunately, a number of very high quality simplified physics models have been developed that are fantastic at estimating reservoir pressurization, to some extent plume migration. This model that we have used has actually been featured throughout the workshop a few times. This is the Nordbotten et al. Model for a single well injection point in which the CO2 plume acts as what we call a gravity current migrating along the top of the cap rock, and it's excellent at estimating the pressurization throughout a reservoir system. And the model that we have developed and made publicly available, it's called CO2 block. We've carried out a lot of analysis to enable essentially a superposition of the pressure response of single injection sites onto each other. There's error incurred in doing that. You can read the papers to understand what that is, but what it means is we can represent a CO2 storage site and ask questions around how quickly we can scale up by adding a large number of sites throughout the region. We can change the distance between the sites, we can change the injection rates between the sites, and so on, and we can do things like optimization or evaluate development plans using this very simple screening tool. So at this stage we have two tools, techno-economic models and physics-based models, and I'm going to use it to ask this question around the scale-up of CO2 storage, and I'll use the UK. You can see the richness of the data that has been created by the British Geological Survey and many others that allows us to really validate this approach. And we'll ask this question, is the scale-up of CO2 limited by techno-economic or geophysical constraints using these models? So just applying our injectivity constraints, what we can say is that the storage units around the UK have sufficient injectivity to support, in aggregate, gigaton per year scale rates of injection. This would be a vast number of storage sites all injecting at once, not necessarily a particularly realistic scenario, but that's a kind of upper limit on the physics-based constraint. While analyzing the physics-based constraints, we did ask the question around how legacy wells might intersect with the CO2 and pressure plumes as a kind of a side study. And for that, we compiled data from the North Sea Transition Authority on legacy wells. Here you can see around 2,200 legacy wells identified in the southern North Sea. And we simply adopted a well risk assessment developed in the United States by the National Energy Technology Laboratory to very quickly categorize risks, and it's a kind of semi-quantitative but mostly qualitative risk assessment on the basis of well age, type, deviation, cement top, and abandonment date. And you can see that the distribution of this out of those 2,000 wells identifies around 18% of the wells as potentially high risk, wells. This database is publicly available with the publication, and there's some validation as well, because there have been development plans published associated with these license applications in the southern North Sea. And what was really nice for us to see was that this very simple screening seemed to align very well with the identification of high-risk wells in the development plans for these sites, and particularly the Viking CO2 storage site. However, you've heard time and again that pressure plumes are much larger than carbon dioxide plumes. In general, that's the case. In these situations, we have applied a kind of fictitious injection scenario. We only consider a regional system with open communication across the region, and this just illustrates one of the results from a planned injection of 325 million tons over 25 years. You can see the pressure plume reaches tens of kilometers depending on the formation that you're evaluating, whereas the CO2 plume, these are very thick formations, reaches scales of order kilometers. And what that means is that this issue of brine expulsion is a concern. The pressure increase that you see is not enough to lift the brine from the formation, from the reservoir unit to the seabed, but it may be enough to begin to expel brine from the well if they indeed leak. On the other hand, I'm not showing the CO2 plume because they would be smaller than the icons I have here for the wells. They're very small, and the spacing of these wells, while they exist in abundance, are of order kilometers apart. And as a whole, it should be possible to find sites where migration of CO2 towards legacy wells can be avoided. So in an aggregate screening, the issue of plume migration is not really featuring in our analysis. Of course, at the site, at the individual project scale, this is really important. So that's not what we're evaluating though. So in any event, so we have these two models, and we've identified injectivity limits to scale up. We have an approach to identifying growth trajectories that are anchored in historical precedent. And so what we've done now is we've combined these models. And what I'll show you is arising is something very valuable in terms of the meaning of storage resource. And to combine these models, what we do is we derive a growth trajectory. In this case, we actually anchor the growth trajectory with the targeted plans from the UK for scale up to 2050. And then we try to fill the growth trajectory with injection using our physics-based model into units around the country. And so I'm first going to show you an example where we've overestimated the storage resource. So this is not the storage resource estimate for the UK. I've multiplied it by 10. So they say that we estimated a static storage resource of 780 gigatons for the UK and simply wanted to achieve this 2050 goal of injection rate. Actually, the combined model would show you very quickly that the growth trajectory can't be met as a whole with injection into the units around the North Sea. There's a huge shortfall. And so in that case, when you've identified that actually this static storage resource is much larger than could ever be accommodated on trajectories that are being considered, what you have to do is then reduce the growth trajectory. And the really powerful thing that happens in this reduction is you reduce the growth trajectory to a point where injectivity limits no longer apply. In other words, you can meet the growth trajectory with the dynamic storage limits. And at that stage, you get a new storage resource estimate. So in this case, the dynamic storage resource estimate that we arrive at is around 500 to 50 to 100 gigatons. And this is precisely aligned with the 78 gigatons that you may have heard over the past few days. It's been estimated for the UK. And there is consistency precisely because the estimates for the UK have been carried out using reservoir simulation. They are, in effect, a dynamic estimate. But what this means is that we can have a combined model which not just provides confidence that growth trajectories and targeted plans can be met, but also that actually redefines what a storage resource estimate should be in a location where less sophisticated estimates of storage resource have been made. So when we reduce the growth trajectory to that which can be achieved with under injectivity limits, you can see how we can fill up some of these key formations in the central North Sea. Another powerful component of this framework is that we can run sensitivity studies. This graph is showing what happens if we reduce the permeability at the extreme ends by a factor of 10 of all of the storage units in the UK, and effectively the storage resource of the entire country reduces from 78 to 55 gigatons. And so if we then apply that around the world, this is a very rapid way to assess what storage resource estimates should be and provide actually a single number still, which is linked to what is possible under dynamic limitations. A very quick identification in our case, for example, that in Australia and Canada and China, where storage resource estimates have been made largely using static volumetric approaches, the storage resource has been overestimated and really should be brought down if we're going to continue to work with single numbers for those values. This is very much in progress. We do not have enough data from all of the sedimentary basins around the world to carry out these dynamic calculations. We're trying to get that information and improve these estimates. And I'll stop there because I'm out of time. Thank you.
Thank you, Sam. Thank you.